This is a smart UPS 1500 that I've turned into an inverter. But not just any inverter, but a 12-volt inverter. It has some issues with startup inrush currents. Now, making an inverter out of an old UPS is hardly anything new. Lots of people have done it in the past, and it's basically just a question of beefing everything up a bit and adding a bit more cooling. But anyone familiar with the smart UPS range is going to have a bit of a head scratcher, because these are natively 24 volts units, and if you hook a single 12 volt battery up to them, they simply will not do anything at all. They'll just sit there as if no battery was connected at all. So there quite clearly has to be some trick to making this work, and the secret on the inside is that this is basically two smart UPS 1500s. Or rather, one smart UPS 1500 and one smart UPS XL 1000. But enough blabbering already, let's get inside this thing and see what makes it tick. And right there you have pretty much the majority of this trick. It's got another transformer installed in the battery compartment. So the gist of the wiring of these transformers is very simple. Their primaries, i.e. the low voltage side, is connected up in parallel, and the output is simply connected up in series to provide twice the amount of winding ratio on the secondary as opposed to the normal UPS. So for 12 volts in, you're able to get about 230 volts out. Modifications beyond that include installing every single possible MOSFET onto here, as well as beefing these traces up and adding another capacitor in there. There are accommodations on the board to do all these things, so it's a very simple modification in essence. In order to drive the extra MOSFETs, I haven't taken any serious measures. I have just connected the gates up in parallel. Since we are just switching MOSFETs, this is going to cause a slightly slower rise time since we're using the original single gate resistor to drive them, but in practice it doesn't make much of a difference. The majority of the power loss in the MOSFETs is actually due to when they're on, due to pure on resistance, since we are dealing with such huge currents. The only non-power related modification done to this unit is actually the paralleling of this resistor over R216 here. This R216 makes up one half of the battery voltage feedback divider for the main processor. And the unit of course runs programming which is designed to prohibit operation on too low a battery voltage in case something goes horribly wrong. So by modifying this voltage divider, the unit will think that there's a 24 volt battery installed, while in actuality there's a 12 volt battery installed. The resistor in question seems to be a 56K. The way the transformers are connected together physically is very straightforward. On the low voltage side they are obviously just connected up in parallel. But on the high voltage side, i.e. the 230 volt side, the original UPS transformer is connected entirely standard to the connector, which is in there somewhere, except for the yellow wire, which has been cut, and rather than going straight into the UPS, runs to the white wire on the new transformer, of which the yellow wire is then returning and going to the UPS. Those are the secondary windings, or the high voltage windings, and that will enable you to get the double secondary ratio on them. The reason it's possible to do this modification so easily on these units has to do with the way the feedback system is designed on them, because there is no feedback from the actual output of the switching transistors, but rather the entire inverter is included in the feedback network. So as long as you have the DC 24 volts, or at least the UPS thinks it has the DC 24 volts on the battery side, and there's 230 volts AC on the secondary, it'll keep going. Because all the regulation is done internally through that regulation loop, it has no reason to actually monitor anything else. Now, a downside of this modification is that I haven't figured out how to get the actual UPS capability working on it. Since these are line interactive UPSs, they have a constantly running AVR functionality to them. So the high voltage side is actually always connected to the grid, and it's monitoring the output of a transformer and using it as an auto transformer to boost or buck the voltage in case you have some surges or sags on your grid. Since we are using two transformers and one is just connected up basically as a single transformer with the only exception of the actual output winding, there's going to be some discrepancy. So if I hook 230 volts into the power inlet on this thing, if it weren't disconnected, the entire thing would just go beep and shut down and consider itself to have an internal error. But this is probably solvable if one puts their mind to it. I just haven't bothered because I built this thing as a definite one-purpose device, an inverter for my solar system. I had no need to actually run it connected to the grid. As for the actual performance of the thing, well, as the two giant fans cut out on the side should bear witness to, isn't too great. At idle it will use about 25 watts just sitting and chugging the inverter along and running the fans, and the efficiency levels you'd get on the load are, on the very low end it will be something like 40 to 60%, and when you're approaching the top output power of about 1000 watts, it will just about to get up to 80% if the weather's alright and the birds are chirping outside. But for the most part, on the medium load, it'll sit at somewhere around 75% or thereabout. So it's not a particularly solar-friendly device, since it's got a high idle consumption and a rather disappointing efficiency. But as a project, if you've got access to a few of these units, you definitely could do a lot worse. I mostly built it as a little experiment to see if it was possible, and in hindsight, well, it certainly is. The things I would have done differently is that the tracks on the board really need to be reinforced. They need to be reinforced a lot because they have run extremely hot, and when this UPS was running under heavy load it would smell very strongly of hot plastic, and that was due to the insulation plastic on top of the board actually melting slightly. The wiring I used for the DC input is 16 square millimeters, which should be good to just over 80 amps. Since it is fan cooled, it'll do the 100-ish amps it draws without any major issues. But really this, it's a bit on the low side. The Anderson connector on the back is just one which came from some unit stock, which has, I believe, dual 6 square millimeter wire coming out of it, which is really too thin to take the whole load of the unit. What I've actually used the Anderson connector for has been to connect a large 45,000 microfarad capacitor to it in order to reduce the ripple. Since even though I've installed the capacitors from 2 units, they are nowhere near big enough to actually handle the ripple which you'll get on the line from a 1-ish meter wire and the extremely strong pulses the UPS will draw under load. So you need to add a lot of capacitance, and the 45,000 microfarad capacitor would solve the turn on instant turn off issue you saw at the start of the video and basically make the unit behave a lot happier. The biggest hurdle by far when making this thing was overcoming the thermal issues and actually getting 1000 continuous watts out of it. As you can see, I've cut out this large hole in the chassis here where one of the fans would just suck air over this transformer to prevent it from overheating, and I've installed these air guides to guide air mostly through here and over here, but also around this transformer here to prevent it from overheating, because these transformers will run very, very hot under long heavy load. They are rated for 180 degrees, but that's probably an internal temperature. I believe I had them running at about 100 degrees externally, or perhaps a bit under that. It's been so long since I built this thing I don't even remember. But you definitely need to keep that in mind if you're making this. You also have giant high current connections here at the heatsink at the output of the inverter, and you need to make sure that this area is extremely clean and extremely flat, else you'll basically have that catching fire. I had to replace one of these air guides once due to the white wire connection there just going so hot it melted it and it went all horrible. And just because I know you want to see this thing actually power something, That's about 800 watts. Let's overload it a bit. That's, I think, 1800 watts heater. Should be throwing an overload by now. Oh well. Let's check the voltage on under the overload condition. Yeah, it's drooping. It's definitely drooping. But since this is using the logic board out of the 1500 VA UPS, it actually isn't throwing an overload condition until we reach just about a kilowatt, and we're just on the brink of that, aren't we? We're just on the brink of an actual overload condition, and the reason that the output voltage and power is dropping is because the battery power voltage is dropping, because we're not connected to a very big battery right now. Ah, there we go. Internal error. When I flicked the lid switch off, it shut down because we probably got too big of a spike on the output. So yeah, this thing isn't 100% perfect, but as you just saw, it works quite well, and the room got a bit warmer since my radiator got to work a bit. And during that brief overload condition, both the top cover of the UPS and the cheap starter cable saw quite a considerable temperature rise. So there you go. I just wanted to make a quick video about this thing before snagging the fans out of it for another project. So I hope you enjoyed watching this, and I thank you for watching. Cheerio. And yes, I am serious about melting plastic.